Hey, students, let's do some more examples of chapter 31. Here was my long list of 9, and I think this worked out pretty good for chapters 29 and chapter 30. That I just don't have enough time in class to do all these wonderful things, and I think you deserve more time seeing some examples. And so I did these 3 in class, and if that's enough for you to go ahead and do the homework, fine. You don't need to see more examples, but if you feel like you're not quite getting it and you need some more extra help, that's why I want to make these videos. So like I did last time, let me take the 9 examples, let me divide it into 3 groups of 3. I already did these 3 in class, so let me do these 3, and later on I'll do another video on these 3, and so again, hopefully you'll have enough resources that maybe you don't need to see all 9 by the time you do all these 9 in the homework, that, hopefully will be enough for you to learn the material. But this can be pretty tricky material here. So let me try number 30 here, and I printed number 30 as well as 32 and 48. Here's 30 here. It gives us a nice little figure, and it's really about Lenz's law. There really isn't any calculation here, but it says a bar magnet is moved towards a loop. Is the voltage A minus B, okay, positive, negative, or 0? In other words, if we take the voltage here and we subtract the voltage here, do we get a positive number or do we get a negative number? Because we know if say, let's say A is bigger than B, then the current would flow in this direction. On the other hand, if B, and I shouldn't have covered it up here, B. If B is at a higher voltage than A, then the current would flow in this direction. And of course, then this would be a negative number. So this is what we would get if the voltage at A minus the voltage at B is less than 0, meaning B is greater than A. And this is the direction of the current we would get if the voltage at A is greater than the voltage at B. And so it really boils down to a question of, which way is the current going? All right, well, I'll come back to the figure here in just a second, but the main idea of this chapter is Faraday's law. And so let's apply the mathematical form of Faraday's law, which is why we call it a Maxwell's equations, because he put Faraday's law, which was in words, into equations. And so here is our equations as we write them today, I should say. And so let me, apply this. And Lenz's law is really that negative sign. It means it opposes, negative, the change in the flux. And so that's where we come in here and we look at the change in flux. And I guess we first have to start, is there even a change in flux? Because we only get an EMF if there is some change in flux. And you can see in the picture, they're showing a bar magnet that is moving towards this ring, I'll call it this orange ring here. And there would be, flux coming from this bar magnet. And so as we got closer, there would be more and more flux. And therefore, there is a change. And so it's safe to say conceptually, without doing any numbers here, that there is a change in the flux. And so there is going to be some kind of EMF. And so this little loop can be thought of as like a little battery, if you will. And so, again, it's going to be looking maybe something like this, where you have A and B. And you could think of this ring as being a battery. And what I don't really know is whether the battery is set up so that the A is positive and the current, flows this way, and then we get A minus B greater than 0. Or if the battery is set up to go the other way, so the current goes from B to A, that would be this, and so A minus B is less than 0. And so I guess that means at first here we can say it's not 0. there is going to be some kind of change in flux. The change in flux does make an EMF, and this is going to make an induced voltage. There is going to be a current. Let's just figure out the direction. Now, let me use the green that we typically use for the magnetic field. The magnetic field comes away from north poles, and in this case, for a bar magnet, would loop around and go to the South Pole. And so in my mind, I'm kind of visualizing that when the bar magnet is far away, there is no flux through this ring. I guess if I take off my wedding ring here and I use something to represent the bar magnet, maybe I will use, what's this? This little metal cylinder as the bar magnet. But when I'm far away from it, I can say there is no flux going through this ring. But if you can visualize a bunch of arrowheads, these green arrowheads pointing in, as I get closer, there would be more and more green arrowheads pointing from my right to my left. And so the flux is changing, and I'll call it the primary flux, from this position of the magnet, and it's getting greater and greater and greater to the left. And so since Lenz's law, it opposes the change. And remember, change really is another way of saying it wants to remain where it is at its same value. So far away, it's zero. And so as you get close, it still wants to be at zero. But clearly it's not zero from the bar magnet coming in. It's making a bunch of flux go to the left. So we conclude that the current would be set up in this ring, either one direction or the other, so that the flux goes back to the original zero. In other words, the secondary flux, and for secondary flux, maybe I'll change colors to red, but we would want the red flux to go to the right as this south pole of the magnet is brought close, so that the total flux through this ring still remains at zero. It opposes the change. And so when we put the two fluxes together, the flux from the bar magnet getting close, and then the current set up in this ring, we're still at zero. And so the red flux comes from the current in here. And so this is where I'm going to do right-hand rule number 2. I'm going to take my right hand, and that's the reason I'm going to place my thumb towards the right, because the flux is going to be towards the right. And so as I look at my fingers are curling around in this direction. And if I'm looking from over here on the right, I would see a counterclockwise rotation. And so in this picture here, I would say the current is going up across the top, down through here, along in this direction, coming to B, crossing through the resistor to A. In other words, B must be at a higher voltage than A, and that really answers our question. Must be negative. And so there is an application of Faraday's law. Well, actually, really, they're just, I guess, the negative part, the Lenz's part, it opposes the change. All right, well, I guess that didn't take too much of my yellow paper, so why don't I just also start number 32 on the same yellow piece of paper, and we'll take a look at it. It says, for the situation shown in the figure, the magnetic field changes in time according to this expression. And so let me just begin here with a little warning that we've said many, many times, and we'll say it again here. When you look at this equation, minus n, there is a derivative of time, and the magnetic flux is an integral in space. And so when we go to calculate this part of the equation, we need to know how B is varying, if it at all, in space and in time. And clearly they show in this expression that it varies with time, but they imply indirectly that it doesn't change in space. And they do that two ways. Number one, there's nothing in here about the position X, Y, or Z in this equation. But number two, they show these X's, the green X's, which are going in for the magnetic field, equally spaced. And that's our visual representation. And so I'm going to take that and infer that this is saying that the magnetic field changes with time, but not with space. And that's going to be important to do this mathematics. Now, we have an R2, which is twice the radius of this little area where there is a magnetic field at 5 centimeters, okay? It says, calculate the magnitude and the direction of the force exerted on an electron located at the point P2 at time equals to 0. Okay, so, well, let me read this one. At what instant is the force equal to 0? And so I guess they don't ask anything about P1 in this problem. I guess it does say it's for problem 32 and 33. So 33 probably has a little discussion about P number 1. But our focus here, and of course the magnitude and the direction of the force exerted on an electron located at point P2. And so if I begin the problem with what we would call the Lorentz force, we would say that any charged particle has a force due to the electric field, and it also has a force due to any magnetic field, so long as the charge is moving. And I think the intent of this problem is really to get you to realize that when you look at this, you might first go, well, I don't know if the electron's moving or not. And even if you say yes or no to that, I think they're implying that the magnetic field is 0 out here. And so this part becomes 0. They say it's just located, so I think they're also saying the velocity is 0. But whether they do that or not, and maybe that's why they were a little more vague, they just want you to realize that you're out here at point 2. The magnetic field is within this little circle of capital R. There is no force due to the magnetic field. But what this chapter is all about is giving us a second way of making an electric field, and that's this Faraday's law. And so if you haven't caught it, let me say it again, as you've heard in my lectures, there's two fundamental ways of making an electric field. The first way is where we spent most of this semester so far with little charges. So if I have like a proton here and a proton here or an electron here, all these charges make electric field, and the total electric field over here is the electric field from these 3 charges. And that's what we've been doing for most of this class time. But now we are learning that there is a second, more sophisticated, more involved way, more interesting way, more useful way of making an electric field. And that is an electric field is created from a changing magnetic field. And that we do have. Although I must admit, this is kind of interesting because the changing magnetic field is over here. It's not here. But so what? I mean, watch this. Let's follow the math. And so I'm going to make a loop to do my integration. And so let me rewrite Faraday's law. And so maybe I'll write it in the, I'll call it the initial form. You might even spread it out and say, well, this flux is actually an integral of the magnetic field over some space, and that's true. But going back to chapter 25 and remembering that the voltage is an integral of the electric field. So if you add up the electric field over some path, you get this connection. And so this involves, three interesting pieces of calculus. We've got an integral over a surface and then the time derivative of that. And on the other side of the equation, we've got an integral of the electric field. And so this has got a lot of tricky pieces, if you will. And as we argued on many of these problems, you're looking for a symmetry or an anti-symmetry. And so let me do this. Let me draw a path and see what the flux is through that path. If a path goes through point 2 and goes all the way around, because when I do this integration, here is going to be my argument. That the physics of whatever is making this electric field, which obviously comes from the changing magnetic field, would be the same no matter where you were on this path. Now again, ultimately I want to know the field at point P2. But by drawing a circle centered around the same circle that the magnetic field is enclosed, I could argue that if I was standing right here, the changing magnetic field that would be viewed from this point is essentially the same as that point. And so whatever the field is at the point I really care about, point 2, would actually be the same anywhere along this ring because of the symmetry involved. And so I'm going to say then that the electric field can be brought out in front of the integral. And although I don't know the value of the electric field, in fact, that's the goal here. Well, I guess the goal is to get the force, and we get that by getting the electric field. And so getting that electric field is a constant over there. And also we've got this argument about this direction, which we can argue here from a symmetry, or really kind of an anti-symmetry, that it has to be either 0 or 180 degrees. I've been drawing lines of symmetry or anti-symmetry in red here. But if you were to draw a line here, and imagine taking this whole experiment and flipping it completely over, the physics you would now see is exactly the same, except the magnetic field's pointing in the other direction. And since it is this magnetic field, or really the changing of this magnetic field, that makes the electric field, we could argue that this flipping over around this line of symmetry, which really then makes it an anti-symmetry, would be exactly opposite. Because everything else is the same. The distribution of the field, the rate at which it's changing, but the direction is different. And so what that would mean is whatever the direction of the field is before I flip it, it must be exactly opposite when I flip it. And that only works when the electric field is at a right angle to this line of anti-symmetry. And in fact, let's see, I think we've been using this kind of orange color, which doesn't stand out too much from the red, for the, what's it been this color, for the electric field. And so that would tell me the electric field has to be perpendicular to this line of anti-symmetry. Can't really see that. Maybe I'll draw it right there. And I hope on video you can kind of see a little different color in this orange and this red. And so if it had been pointing, say, in this direction, and you flip it over, it now points in that direction. But see, that wouldn't work if it was pointing this direction, or if it was pointing this direction, or if it was pointing that direction. And so we did the same thing with Gauss's law, although Gauss's law, we had lines of symmetry, so they had to be along the axis of symmetry. These are lines of anti-symmetry, so they have to be perpendicular to them. But though what that does tell me, though, is that the direction of the electric field is the same direction as this blue line. And the orange line and the blue line are in the same direction, and that's what this dot product is. And so we can argue from these lines of anti-symmetry. And we can do lots of lines of anti-symmetry. I mean, we can do it here. We can do it here. We can do it here, and here. And so we come to that conclusion that the field, being perpendicular to the line of symmetry, then is in the same direction as the blue, and that's what this dot product is. This is between the electric field, which is that orange, and then the ds, which is this blue loop. And then this plus minus, if we don't worry about 0 versus 180 degrees, then we can just say this is the magnitude of the electric field. And then this is the integral of ds, which would be the 2 pi, and then this would be radius r2. And so that would be the left-hand side of this calculation. Now, on the right-hand side, and since I'm already doing a absolute value, I'll ignore the negative. I'll put in n equal to 1. And then I have a time derivative. And then I have the amount of flux. And then it's the flux that goes through this loop. Okay. Well, coming back here, that loop is pretty big. In fact, it's bigger than the whole area where there is a magnetic field. I guess if you wanted then to break it down into two integrals, where the first integral involved the area within capital R, and so I'll just call that area 1. And the second integral would be the area that is beyond capital R and out to R2, so I'll call that area 2. The field, maybe I'll do area 2, the field would be 0. And then, of course, the field would be non-zero within this little piece. And what I'm getting is might be just so obvious that I don't really need to consider the whole area, even though that equation says, yes, do the whole area where there's a magnetic field. Well, it says do the whole area that's, enclosed by this loop. But because there are parts that don't even have a magnetic field, those are going to go away. And so we only need to be worried about where there is actual flux, and that would be just to capital R. And then likewise, and so let me just jump down to this line 1. Here's the time derivative. And this is where I was saying that the implication here is that the magnetic field does not change with area, so I can bring it in front of the integral of area. But it does change with time, so I can't put it in front of the derivative of time. And of course, this is then just the integral of b, and then this would be area 1. All right, so we've got electric field, we've got 2 pi r2. And then here, I might as well just go ahead and take area number 1. and put it all the way in front, and maybe even write it as a pi times capital R squared, since this would be this area. And then I would have the time derivative of, and then we've got 2t cubed minus 4t squared plus 0.8. And maybe I'll just do a little bit of simplification, but not too much yet. And so we've got 2 times R2. We've got R squared. And then here's this derivative, which would be 6t squared minus 8t. And then derivative of that would be 0. And of course, now I can bring the 2R2 over, and I have an equation for what is the magnitude of this electric field. So let's see. It looks like R2 being twice R and being 5 centimeters means that R itself is 2.5 centimeters. So let me write that as 2.5 and square it. And then over here, I'll take 2 and divide it by R2, which is 5 centimeters. This would be 6, and they do say at a given time. So calculate the magnitude and direction of the force on the electron located at point P2 at 2 seconds. So 2 squared minus 8 times 2. All right, well, 8 times 2 is 16, and 4 times 6 is 24. And so 24 minus 16 is an 8. All right, so in terms of magnitude, I have 0.025 squared divided by 2 divided by 0.05, and then times an 8. And so it looks like I've got a 0.08. Now, I haven't been putting in all of my units here, but I don't know if you want to call this a volt per meter or newtons per coulomb. Probably, since we're dealing with force, newtons per coulomb would probably be the better of the 2 units for this setup. And so when we go to calculate the magnitude of the force, we would say just Q times the magnitude of the electric field. And since they say it's an electron, we know it's charged. So I'll take the field and multiply by 1.602 times 10 to the negative 19 and come up with a magnitude of a force of 8.01 times 10 to the negative 21 newtons. Now, I'm not quite done because I haven't done anything about direction as of yet. Okay. And I kind of lost the ability mathematically to do directions right here when I ignored the pluses and the minuses and the 0 and 180 degrees. But that's where the Lenz's law comes into nice fashion here. Okay. So let's come back to this picture here. And we might have to have a little bit of a calculation here on, what this function looks like, because we need to know then, is the field increasing or is the field decreasing at this point? And so I guess there's a couple ways we could do it. We could take a moment in time just before and just after the 2 seconds. Might be better to look at the change of the magnetic field. That is, how is the field changing with time? Because that's what we already did. Isn't this the field? And so it is saying it has a slope of 8. So if I had a grid of the magnetic field and time, and at 2 seconds, I know it has a slope of 8. So I know the strength of the field is increasing, okay? Now, I just threw it in the first quadrant. I really don't know its value. I suppose I could do that. Let's just see what the field is at 2 seconds. Because 2 cubed is, 8? And 8 times 2 is a 16. And then a 2 squared is a 4. And 4 minus 4 is a minus 16 plus 0.8. Okay, so the field is, something like 0.8. It's not that, well, in Teslas, that's a pretty strong field. But numerically, that's not very big. And so maybe I should have put in my graph it down here and going like that with, again, a slope of 8. But again, where it is on the graph didn't matter as much as we knew the change was 8. The change was increasing. And so coming back to here, then my field, and I suppose, we can debate on what they actually mean with this picture. Is this the direction of the field at what? Time equals to 0? Or is this the direction of the field at 2 seconds? I'm going to take it to believe this is the direction of the field at 2 seconds. So they're showing it in, and I'm calculating a positive number. And so because of that, I'm going to call into my paper the positive number. Okay? And so I have the field going in, and it's increasingly in. And so there's more and more and more flux. Call this the primary flux. Because if there had been a wire here, and I know there's not a wire here, but if there was a wire, the EMF that's produced would create a current, creating a secondary field that opposes the change. And so if the flux here is getting bigger in, the secondary flux would be out. So I'm going to take my right hand and point my thumb out and then say the current would go around in this direction. And of course, there would only actually be a current if there was, some kind of a wire here with electrons that can move. And since we don't really have a wire, but we know that the current would be in the direction of the field, this works for also saying what the direction of the field would be. And so the field would be in a counterclockwise direction. Okay. And then since we also know that the force on an electron, because it is negative, is opposite of the direction of the field, the force, if I could put that in a different color, I don't really have any colors left, but if this was an electron, the force then would be opposite of the field. And so that would be a clockwise direction. And of course, this kind of assumes that they're drawing the field not only uniform, but more importantly, what direction is it when t equals to 0? Okay. Now, that might be the harder part of this, but if I continue on to part B, you can kind of see at what instant is this force equals to 0. Well, force would be equal to 0 when the electric field is equal to 0. The electric field would be equal to 0, which is the whole point of this chapter, when the changing magnetic field is 0. And so when does dB dt equal to 0? And again, we took that derivative. Where is it? Right here. It's a 6t squared minus 8t. And so since it's quadratic, there should be 2 times that it equals to 0. In fact, I can factor out a t. And if you have 2 factors that come out to be 0, one option is when t equals to 0. And the other one is when 6t minus 8 equals to 0, or 6t equals to 8, or t equals to 8 over 6, which I guess is 1. And we have 2 over 6 and a third. And I suppose I could give us some more insight to this graph of what the magnetic field looked like. Because the equation for the magnetic field is cubic. And a cubic equation, as you probably recall, would have something like that. And so something like that would have 2 places where the slope is 0. And so the slope would be, this one right here at time equals to 0. And of course, you could even come back here and see that at time equals to 0, it has a value the same as 2 seconds, which is right here. And at 1.33 seconds, the fields, that'd be kind of a fun one to do, but I'm kind of getting off base here, going down a rabbit hole. 2 times 1.3333 raised to a power of 3 minus 4 times 1.3333 squared plus 0.8 is a negative, about a 1.5. So let's see if this is on my graph 2 seconds, and this is about 1 second. 1.3 is right about here and maybe drops down to there. So roughly, I have a magnetic field that looks like that, where it is no changing at 1.33 seconds and no changing at 0 seconds. Actually equals 0 3 times. There's 3 roots, sure. Not always real roots, but in this case, it looks like my graph, these would be real roots. And so there it is. But of course, how it was changing at 2 seconds was the crucial one to this problem. All right, well, we could analyze more on the magnetic field and kind of have fun with this one, but let's move on and stay away from that rabbit hole. So my third one, at least for this video, was number 48. And 48 is a little bit like this 32 in the sense that we need to find the EMF, and then this would be the EMF. Well, what we have here is 2 infinitely long solenoids, but you only see their cross section. And so maybe to understand the problem a little better, let me grab my little solenoid here. But they're saying we have one solenoid that looks like this, and the current is flowing so that the field goes in. And so taking my right hand and curling it with my thumb pointing in, this represents one of these infinitely long solenoids that are really extending in and out of the screen. Now, the other solenoid has a little bigger radius, maybe I'll use this one to be my second solenoid. I'll kind of wrap it around my finger. That'll be about the same diameter there. And so again, it too is going in and out of the screen. But here, so that the field comes out, so my thumb on my right hand would say the current is going around in this direction. Now, I don't know if that really matters, because I think ultimately, and I got to keep reading the question, they're going to be asking for the current in these resistors that are surrounding these solenoids. They're not even touching these solenoids. And that might be part of the important lesson here, because we've been doing problems involving currents where our wires are connected to our batteries, and our batteries get their voltage or their EMF from their charges. And the lesson here in this chapter is that there is two ways of making an electric field. I'll call it the first way you learned with these charges, and that's why we had batteries, and we had like our lithium ion battery. And what was nice about our lithium ion battery is, the lithium ion is what made the electric field. But that was just one way of making an electric field. Now we're making our electric fields by a changing magnetic field. And the changing magnetic field doesn't have to, actually touch it. As you saw in this problem, the electric field is outside of the solenoid. And so, this is, not metal to metal contact. Many of you probably have these chargers where you put your cell phone down on the mat, and it, produces then an EMF through the mat and even through your case on your phone, and then, and induces an EMF inside of the phone, which charges the battery. And so there's some nice aspects to that. And so that's, nicer than just having a metal to metal contact. And so there's a lot of important and useful reasons for that. But let me not go down too much into lecture mode here. And I guess we could say the current in that solenoid goes around this way. But again, I don't think that's going to be relevant. It's going to be whether or not the field is increasing or decreasing. All right, so let's keep reading here. So two infinitely long cylinders seen in cross sections pass through the circuit as shown in the figure 48. The magnitude of the B field inside each is the same and is increasing at a rate of 100 Teslas per second. What is the current in each resistor? All right, so this right here obviously has a resistor of 6 ohms, a resistor of 3 ohms. And what they're trying to get at then is this creates an EMF. And that would be as if it is a little battery here. And so I will use the battery symbol. I just haven't decided yet if I should put the battery symbol this way so that the current flows in a clockwise direction, or if I should put the battery symbol this way. And that's where our Lenz's law is going to become important here. Okay, so which way is the induced EMF? And so Lenz's law says it opposes the change. So let's start with what we have to begin with and see how it is changing. So what we have to begin with is a field going into the screen. And it says its magnitude is increasing. So it's more and more into the screen. So the secondary field opposes the change. So if you're having more and more into the screen, the secondary field is going to come out. And so if I take my right hand with my thumb pointing out, my fingers would be going in a counterclockwise direction. And so I will put the battery, this one, I'll call that EMF number 1. And I can change this picture, if you will, of a changing magnetic field to one that has a battery, an EMF. Again, this is an EMF not created from charges like we were first exposed to when we did currents in chapter 27, but an EMF that is created from Faraday's law. And let me do the same thing here, that in my other loop here, so here's my 5 ohms. I have, again, I'll just put a little gap here. I will call this EMF number 2. Because again, around this one, there is an EMF of some kind. Okay? And again, that EMF has to do with the change. Now, in this case, the field is, again, increasing coming out. So it's already coming out. And then more and more is coming out. And so the induced field will want to oppose that change. So it wants to get back to where it was. So that means it's going to make some going in. And so it's going to want to make the current go in this direction. And so the plus is going to be on this side of the equation, if you will. All right, so that's how I can decide, I'll cross these out now, whether or not to put a battery in one direction or in the other direction. Now, of course, now I need some numbers here. And so maybe I'll jump over to my yellow pad here, because the EMF, and I'll just say EMF number 1, is equal to the negative of, and maybe I'll just put magnitude and ignore the negative, the number of loops of wire we go around, which for this case is 1, times the change in flux through this loop. And in my case, you can see that we would have just, if you let me kind of jump past all those other equations we've been doing, B dot dA, technically the flux would be everything within this big old square here. But we could divide this integral into 2 pieces, the part involving this circle and the part involving everything else. And the part involving everything else, the B field would be 0. So I'll call that area 2, where this would be B times area 1. And so really, because the B field is at 0 for all of this, none of that really matters. It's the same EMF when you go around it, whether this is a big square, a little square, a hexagon, a polygon, a circle. So that's kind of nice to realize we don't have to have an exact circle in here. It would mean, though, that, we would have difficulty defining and calculating what the electric field is at each point, because we didn't have that beautiful symmetry argument that we had in 32. But they didn't ask for the electric field. They asked for the whole EMF, and the whole EMF is the integration of the whole field. So we kind of avoid that complication. And then, of course, the area number 1 doesn't change, and then we just have the derivative of the magnetic field. And that, fortunately, is given to us. And so area, and I'm pretty sure that's why the author gave you the area of the square as well as or at least the dimensions of the square, so you could get the area of the square, and the dimensions here of this circular space, so that you could get the area, and wanted to see which area do you get, but this would be the area where there is flux. So this would be pi times a radius of 0.1 squared. This would be just, as we said back here, the area where there is a field. And then the rate at which the magnetic field changes is what they gave you right here. The increase in the field is 100. Oh, that's kind of nice, because a tenth squared is 100th, and 100, those cancel off. And so this just becomes pi volts, which is 3.1415. Okay, so this is the voltage that I would put right here, voltage of pi. And let me do the same thing here for number 2. And so the voltage magnitude of number 2. And our argument goes all the same thing. It's pretty much the same song and dance. We don't worry about the negative. We have one loop. We're going to take the derivative of the flux. The flux is technically the whole square, but if we divide the square into the part where there is a field and where there's not a magnetic field, the part that doesn't, it doesn't matter how big or small it is, it has a zero field, so it goes away. And so what we end up with is what I'll call, again, area 1 and then dB dt. Here the number's a little different because the area where there is a field is a little bit bigger, so there's more change in flux. Not because the field is stronger, because they do say it's the same field, and not because it is changing at a faster rate, but just because it has more area. Remember, flux is both the field and the area and the angle, and the angle is the same. So these are almost identical, but you do have more flux here just because there's more area. So this would be 0.15 squared, and then times the changing field of 100. And 15 squared is what, 225? So 0.15 squared, and then times 100 doesn't quite cancel off. In fact, it now becomes 2 times, or 2.25 times pi. So times pi. And so this is about a 7.07 volts. Okay, so 7.07, and maybe I should put this as a decimal, 3.14. And that's really the hard part, or at least the new stuff, and probably why your author gave it a magenta color, is because there was some pretty hard stuff in here, getting the EMF and then treating it like a circuit. And now we're ready to treat it just like a DC circuit as we did in chapter 28. And so we still got some work to do here. And so let's do our KVL. Maybe I'll start here and go around. So it would be plus 3.14. Oh, I should label some currents first. Let's say this is jetting a current of I1, and this is jetting a current of I2. So they come together and merge and become I3. And so our left loop here is 3.14 minus 6I1 minus 3I3. That equals 0. And our right loop, if I start here and go clockwise, would be 7.07 and a plus, minus 5I2 minus 3I3 equals 0. And that's our two loops. And then the KCL would be at this node where they combine. And so I1 and I2 come in, and I3 comes out. And now I'm left with a question. I've got 3 equations, 3 unknowns. Do I do it with the calculator or do it by hand? Maybe I'll do the calculator here. This one's not too bad because I could easily put I3 into there and have a system of equations that's quite reasonable. But I'll go ahead, since I've been encouraging you guys to just use the power of your calculator and do your matrix. So let me write this as a matrix equation. I1, I2, I3 equals. And so I'll start with this one, kind of imagining these two on the other side, so they become positive. So if I would have 6 times I1, 0 times I2, and 3 times I3 equals 3.14. And so that would be this first equation written in a row column matrix here. Same thing here. If I imagine these on the other side, I would have 0, I1. I'd have 5, I2. I'd have 3, I3 on that side. And then this side would be the 7.07. And the last equation will be 1, 1, and negative 1. If you think about moving this to the other side, I get a 0 over here. And a negative 1 for I3, and 1 and 2 is a positive 1. And so if I go ahead and take advantage of the matrix features on my calculator, I'll come over here to edit and write it as a 3 by 4 matrix and just kind of enter in a 6, a 0, a 3, a 3.14. Next line would be a 0, a 5, a 3, and a 7.07. Last line would be 1, a 1, a negative 1, and a 0. And it's kind of nice to double check these. I'll just go that first column good, that column good, that column good, and that column good. And so that's matrix A. And then sometimes it just helps mentally just to say, okay, let's quit that. That's matrix A. So now what do I want to do with matrix A? Well, matrix A, I want to do a little math to it. It's called, put it in the reduced row echelon form. So the calculator will manipulate this left-hand side of the matrix. And it'll do all this matrix calculator stuff. And like any math, what it does to the left, it has to also do to the right. So whatever it has to do to get to the identity matrix, it changes this side. But what's really nice then is you can see when you have the identity matrix, whatever number is here is I1. And whatever is here is I2. And whatever here is I3. And so I will use that reduced row echelon form operation. And of course I have to say, well, what matrix do you want it to operate on? Yeah, so I want it to operate on this matrix, matrix A, and so hit enter. And so there's the identity matrix, and so there is current I1 at 0.062, I2 is 0.86, 0, and I3, it's off the screen here, is 0.923. Or maybe I'll leave it as a 2 so that these two add up to that one as they should with a little bit of rounding. Okay, well, I hope those were good. And did I finish that problem? I think so. Yeah, what is the current in each resistor? And so I've got the 3. All right. Take care, and I hope those 3 helped in some way. Bye now.